Welcome to This Explainer. Okay, we are diving right into this today because we are unpacking what is honestly the most thrilling scientific detective story ever told, the complete journey of atomic discovery. Seriously, forget whatever you think you know about basic chemistry. We're going to look at the clues, the false leads, and the massive breakthroughs that literally rewrote our entire understanding of the universe.
To really grasp the rigorous chemistry and physics you're tackling in Class 11, we first have to step back and answer this incredibly mind-bending question. How do these tiny, completely invisible, and deeply mysterious subatomic entities actually come together to build the solid reality we interact with every single day? It's a puzzle that took some of the absolute greatest minds in history to solve.
So, here's our roadmap for today's explainer. We'll start with unlocking the subatomic mystery, then watch the rapid evolution of atomic models, decode the secrets of spectra and radiation, cross over into the bizarre quantum realm, and finally, land on the exact rules for electronic configuration.
Let's start with Section 1, Unlocking the Subatomic Mystery, Identifying the Hidden Players. You know, for the longest time, atoms were thought to be totally indivisible, like the absolute smallest chunks of matter possible. But the first major breakthrough was realizing that atoms themselves are actually made of even smaller pieces. J.J. Thomson kicked things off by discovering the negatively charged electrons. Then Rutherford found the heavy, positively charged protons concentrated right in the center. And finally, James Chadwick discovered the neutrons, which are those neutral heavyweights sitting in the nucleus. Once we had our cast of characters, the real work began.
That brings us right to Section 2, Evolution of Atomic Models. Upgrading our understanding.
Okay, I want you to think of these models almost like software updates. Each new version patched a major bug in the previous one. In the early 1800s, we just had Dalton's solid, indivisible sphere. But once Thomson found the electron, he upgraded us to the plum pudding model, imagining negative electrons scattered around in a positive soup. But then came 1911. Rutherford fired particles at gold foil and realized most went straight through, but some bounced back. He literally said it was as incredible as firing a 15-inch naval shell at a piece of tissue paper and having it come back to hit you. Crazy, right? This completely shattered the plum pudding idea, proving atoms are mostly empty space with a super-dense nucleus. Finally, in 1913, Niels Bohr organized those chaotic electrons into specific, structured circular orbits around that nucleus.
Real quick, before we go any deeper down the rabbit hole, it is absolutely crucial for your exams to lock down these definitions. This is our Atomic Properties Dictionary, and it lets us categorize atoms based on their specific particle counts. The atomic number is your proton count, while the mass number adds in the neutrons. Then we have isotopes. They have the same protons but different neutrons. Isobars share the same mass number but are different elements entirely. Isotones have the exact same number of neutrons. And isoelectronic species, those are atoms or ions that have the exact same number of electrons. Definitely memorize these because they're basically the vocabulary of the atomic world.
Moving right along to Section 3, Decoding Spectra and Radiation, Using Light as a Clue. To push beyond the Bohr model, scientists couldn't just look at the atom directly. They had to become detectives of light. So how do electrons actually behave in those orbits? Well, analyzing concepts like blackbody radiation helped figure that out. Think of an electric stove burner heating up. It goes from dark to glowing red to white hot. Analyzing how that light works gave researchers their first massive clue that energy within an atom isn't just a smooth, continuous flow. It's quantized, meaning it exists in specific, discrete packets. The atom wasn't just a tiny solar system, it was a machine governed by very, very strict energy rules.
When we look at the spectroscopy of atoms, we see this brilliant contrast. On the emission side, this happens when an electron falls from a higher energy state down to a lower one, and it releases that difference in energy as a literal flash of light. On the flip side, absorption spectra are the exact opposite. An electron absorbs a very specific wavelength of energy to jump up to a higher, excited state, basically stealing that light and leaving distinct, missing black lines in the spectrum. It is exactly like an atomic fingerprint.
So let's look at how this applies to the absolute simplest atom we have, hydrogen. We can map the hydrogen line series, showing exactly what type of radiation is emitted depending on which shell the electron lands on when it falls. It's a crucial thing to memorize, but the pattern is actually incredibly logical. If the electron drops all the way down to the very first shell, it releases a massive amount of energy. That's UV radiation, known as the Lyman series. If it lands on the second shell, it's the Balmer series, which is visible light. Landing on the third, fourth, or fifth shells gives us the Paschen, Brackett, and Fun series respectively, and all of those release lower energy infrared radiation.
But just as we thought we had the atom perfectly mapped out with predictable orbits and neat energy levels, the clues led us into Section 4, the bizarre, mind-bending quantum realm. Up until this point, we were treating electrons like tiny, solid planets orbiting a sun. But then Louis de Broglie comes along and introduces wave-particle duality with this formula. Wavelength equals Planck's constant divided by mass times velocity. He proposed that any moving particle, especially incredibly tiny ones with almost no mass, like electrons, actually has an associated matter wave. They aren't just localized points anymore. They exhibit wave behaviors like diffraction and interference. And incredibly, this totally bold hypothesis was later proven absolutely correct by Davison and Germer, who demonstrated that electrons do in fact produce diffraction patterns just like light waves. Wait, electrons act like waves? Yes, they absolutely do. And this completely shattered the old planetary models. Why? Because you can pinpoint a solid particle. You know exactly where a planet is in its orbit. But a wave is completely spread out. You simply can't pinpoint a wave the same way.
And because of this strange wave nature, Werner Heisenberg realized we face a hard mathematical limit in our detective work. The uncertainty principle states that it is fundamentally impossible to determine both the exact position and the exact momentum of a subatomic particle at the same time. The more accurately you know where an electron is, the less you know about where it's going, and vice versa. It's a fundamental rule of nature.
So, to solve this massive uncertainty problem, physicists had to completely abandon the idea of strict, neat orbits. Instead, we moved to orbitals, which are basically regions of space where an electron is highly probable to be found. And to describe these probability clouds, we use these 4 quantum numbers. Think of them as the ultimate subatomic zip code. The principal number tells us the main energy level. The azimuthal tells us the shape of the orbital. The magnetic tells us its orientation in space, and the spin tells us which way the electron is rotating.
Now that we have our quantum numbers and we understand orbitals, we arrive at our final part, Section 5, Rules of Electronic Configuration, the ultimate subatomic address system.
Let's see how all of this builds a complete picture. By following this strict 3-step logic, you can flawlessly write out the electronic configuration for any element on your test. First, the Aufbau principle. Electrons are basically lazy. They always fill the lowest available energy levels first. Second, the Pauli exclusion principle. An orbital can hold a maximum of 2 electrons, and they have to have opposite spins, meaning no 2 electrons in an atom can ever have the exact same 4 quantum numbers. And third, Hund's rule of maximum multiplicity. When you have multiple orbitals of the exact same energy, electrons are going to fill them singularly first before they start pairing up.
Just a quick pro tip before we wrap up. As we're working through these concepts, make sure to keep a formula sheet handy. You're going to need it for quick calculations regarding things like the Rydberg constant for those emission spectral lines and the angular momentum formulas dictated by our quantum numbers. These aren't just abstract ideas. They are the highly precise mathematical tools that make all of these models actually work on paper. As we close out this explainer, I really want to leave you with this thought. As you apply these formulas and rules in Class 11, let yourself step back and wonder for a second. If the very foundation of matter is built on these deeply uncertain, wave-like particles darting around in mostly empty space, governed by bizarre quantum probabilities, how do they perfectly collaborate to build the completely solid reality you are sitting in right now? It's a totally fascinating question, and it's the exact reason why the study of atomic structure is so incredibly rewarding. Keep that curiosity alive, keep studying those properties,